So I'm Bill Dewey. I work for Taylor Shellfish Farm. The Taylor family and Taylor Shellfish Farms, for people who aren't aware, we're a fifth generation shellfish farming family. I've worked for the Taylors for 20 years now. They started in 1890 in southern Puget Sound and have grown in recent years to own farms throughout Puget Sound, out on the Washington coast, up in British Columbia. We have a hatchery here on the Hood Canal. I'll talk about another hatchery over in Kona, Hawaii, a big nursery facility down in Humboldt Bay. So a large producer of farm shellfish, and definitely a vested interest in this issue of ocean acidification, as you'll see. So just so you have an idea of the investment in the shellfish industry here in the Pacific Northwest, I just wanted to walk you through some photos of what we're about. As Eric mentioned, Washington State leads the country in farm shellfish production, and so I just want to show you a little bit about what that's about, talk about the oyster seed production problems we've been having related to ocean acidification, what we're doing as a company and as an industry to address it, and then just finish with one slide on sea level rise. So on the west coast of the United States, mostly it's small or medium-sized family operations from Alaska to California, and Washington leads for one particular reason, in my opinion, or one fundamental reason, and that's our ability to own our tidelands. So this is a typical map of a lot of our shellfish producing bays in the state. This is Samish Bay up in northern Puget Sound, and shortly after statehood, Washington legislature passed laws that allowed for the purchase of tidelands into private ownership, specifically for the purpose of culturing the native oyster at that time. They were trying to stimulate an industry to replenish what was being depleted in the 1800s from the wild fishery, and it was very successful in that endeavor. And laws later changed to allow us to grow other species besides the native oyster, but that ability to own our tidelands is really fundamental as to why we have such a successful industry here today. I forgot to mention that besides the work I do for Taylor's, I also have a shellfish farm of my own. And up here in Samish Bay, I grow Manila clams on the weekends and in my spare time as well. So, bottom culture of oysters, clustered oysters, has been a long history of our industry for shucked oysters, shucked meats. That's been our traditional industry. It's shifted in recent years. I'll talk about that. These are more of those clustered oysters up on long lines. When their bottom's too muddy, we support the crop off the bottom. We've transitioned, a lot of the industry has transitioned in recent years to single oyster culture. This is just an example of growing single oysters on the bottom. Areas where you have predators, you have to protect those little baby single oysters, so they grow them in bags such as these in the lower right. These are a different method that's evolved in recent years to grow what we call, this is what Taylors call our shigoku oysters. So these are single oysters growing in bags that have buoys on them. So as the tide comes and goes, the bag rotates up and rotates down, rotates up and down, and that constant movement gives the oyster a really smooth shell and deep cup, and a really popular characteristic for the half shell trade. Manila clam culture, we grow about 9 million pounds of Manilas here in the state every year as well. This is a picture from my farm here in the lower left. Mussel culture we do on rafts. We got Pen Cove mussels up on Whidbey Island, one of our big mussel farms in the state. Taylors have 2 farms down in Totten Inlet in southern Puget Sound. And then finally, geoduck clam culture. This is a more recent species for us. The industry's been farming these since the early 1990s. So the industry relies today mostly on hatcheries for our seed production. Some is collected from the wild, but by and large we rely heavily on hatcheries. This is Taylor's hatchery on the Hood Canal that we built in 1989. And basically, you're probably all familiar with this by now, but from other talks, but the shellfish life cycle, the first few weeks of their life, they're plankton, they're free floating in the water. So they release their sperm and eggs into the water. Fertilization happens externally in the water. They go through a series of plankton stages before they settle out of the water column to the bottom, where they go through a metamorphosis and begin their life on the bottom. In the case of oysters, they secrete a cement and they glue themselves onto something. From an evolution standpoint, the preferred substrate is oyster shell to do that. So in the hatchery, we basically bring the adults in, we condition them, we spawn them, we rear the larvae in these big fiberglass tanks. This is a picture of some oyster larvae in the middle here. No artificial food for the guys, for these shellfish in the hatchery. So a big part of the work in the hatchery is growing multiple different species of phytoplankton to feed them. This every few days they change the water in these tanks, and this is just siphoning the water through a 75 micron screen. And that brown haze on that screen, for those who can see it, it's kind of down low on the slide there, is probably a few million oysters that are being captured there, and they'll refill the tank and put those larvae back in there. For single oyster seed and for Manila clam seed, we need an intermediate step between the hatchery and the farm to get the animals a little bit bigger. When they leave the hatchery, when they end that plankton stage, they're only 1/4 millimeter in size. And so if you put them out on the farm, they're gonna get blown away in a storm or eaten by a predator. So we have nursery systems to boost them up, to get them up to, say, thumbnail size in the case of oysters, where we can take them out on the farms and have pretty decent survival when we plant them out. This is our hatchery over in Kona, Hawaii. We went over there actually about 15 years ago, because it's an easier place to grow babies. In Washington State, in the wintertime, the sun goes out, the water gets cold, and things stop growing. And we would fight Mother Nature all winter long with our greenhouses and heating up the seawater and not very successfully. And we realized 15 years ago that these things are tiny. We can put a lot of them in a little 6-pack beer cooler. You can put 20 million oysters in a 6-pack beer cooler and fly it anywhere in the world. So we thought, let's go someplace warmer where it's easier to do this. And Kona's got 330 days of sunlight a year, and it's in an aquaculture park that's got hot and cold running seawater. It's just a really easy place to do this. And the air freight's insignificant because the animals are so small when we're moving them back and forth. So it's turned out to be a very valuable facility, both from a seed production standpoint, but then with ocean acidification, as our production has collapsed at a couple of key facilities here on the West Coast, the Kona production has turned out to be extremely important. And we've been expanding our capacity over there to offset our losses here. Dewey clams, just some more infrastructure development for raising baby clams there. So back around 2006, we started to experience problems with our oyster seed production, but early on we thought it was a bacteria, naturally occurring marine bacteria, Vibrio tubiaceae, that was causing that problem. We soon realized, after developing very expensive filters to get that out of the water, that there was something more serious going on, and Dick was the one who turned that light bulb on for us and drew the attention to ocean acidification. He was our keynote speaker in 2008 at our Shellfish Growers Conference and delivered the very somber news that, what's killing your oyster larvae is, in some cases it's this tubiaceae for sure, but actually that tubiaceae is just created by these conditions that are caused with upwelling, and with that upwelling is this corrosive seawater that's killing your larvae. And probably the worst part of his message for us was, oh, by the way, even if we can convince the world to stop emitting CO2, which is the source of this problem, there's enough CO2 already absorbed in the Pacific Ocean coming your way that it's going to get worse for 30 to 50 years before it starts to get better. So not great news. We've been fortunate since then to have some luck with monitoring and adaptation, which I'll touch on, but this is just the phenomenon that we have here on the West Coast. With these north winds, we get this upwelling effect that brings these undersaturated, low pH waters to the surface. They come into our estuaries, come into our intakes in our hatcheries, and it affects our ability to grow our oyster seed. The two main facilities, we only have a few hatcheries on the West Coast to supply the entire industry with their seed. And Taylor's have one of them in Dabob Bay here in Washington State, and another major facility is the Whiskey Creek Hatchery in Netarts Bay in Northern Oregon. Both of us experienced serious losses starting around 2006 in our hatcheries. And this is just some graphs. These are a bit dated. I need to get these updated to show what's happened in recent years. But you can see the pretty steep decline, certainly at Whiskey Creek. Taylor's is maybe lower than most of you can see, but it's a similar slide there. A little more confusing. The white bars within the blue bars are actually things that we did to increase our production capacity in our seed facilities to offset the losses that we were experiencing from the mortalities in Dabob there. At the same time we're having troubles in our hatcheries. There's a big portion of our industry out in Willapa Bay that relies on catching natural recruitment, not using hatchery seed, but just putting oyster shell out in the bay at a really critical time to catch the baby oysters that are settling. Well, we went through a 7-year dry spell here starting in 2005 with no natural sets. So besides 2 of the hatcheries collapsing, are having major drops in our production. The natural sets failed as well. So a really serious oyster seed shortage for the West Coast oyster industry. Well, the research that's been going on has helped us understand better what's happening. You know, we've observed in our hatcheries that the greatest amount of mortality is happening in the first 2 days after fertilization, and we didn't really fully understand why that was happening. And Oregon State University, some of the research there has helped bring that into focus. We didn't have that aha photo, that pteropod photo of oyster larvae. And so the blue ribbon panel actually was the impetus to go get that scanning electron microscope image so we could show people what was happening to our baby oysters. And frankly, it was an eye-opener to us. We hadn't been able to see this. We see, you know, we look under our microscopes in the hatchery and we see dead oysters, but we can't see them in a magnification that's great enough to say, you know, what happened? Why are they dead? So this was a very telling image for us to see that the oyster larvae on the left is one that is grown in good seawater conditions, pH of 8.2, high aragonite saturation, and low CO2. And on the right is a pH of 7.5, CO2 levels up around 1200, and a low aragonite saturation. So what happens is in the first 2 days of life, 90% of the oyster's weight that they're putting on is shell. Once that egg's fertilized, it needs a skeleton to protect itself. So 90% of its weight is shell, and it does that all with energy from within the egg. And then it also has to develop its feeding mechanism with that energy that's within the egg. Well, if the aragonite saturation is low, it has to work really hard to get those calcium carbonate ions out of the water to build that shell. It struggles, and the result is this deformed, imperfect shell, and then it runs out of energy before it develops its feeding mechanism, and so it dies. Or if it makes it, it's hurt. You know, it's limping because it hasn't developed things correctly, and so then our seed doesn't do well. So here's the oyster larvae, that feeding appendage that's referred to as a velum there, that it motates with and feeds with. Here you can see under a microscope in the hatchery, you get an idea of the importance of that appendage for these young oyster larvae. That's what they're feeding with and motating with when they're in that plankton stage. Once they end the plankton stage and go through metamorphosis, they lose that velum and start feeding with their gills. So for the industry, you know, after Dick Feely's talk, of course, the reaction was panic. And then since then, we've been really busy with adaptation. We recognize that if it's going to get worse for 30 to 50 years, our fate's pretty well sealed. So we better get busy learning how to adapt to it and be fluid so that as it gets worse, we can continue to adapt to it. So definitely have ramped up the research and monitoring at our hatcheries. We've expanded, as I mentioned, our larvae production in Kona. We've been having some great success this year. Both us and Whiskey Creek this past year added automated treatment systems into the hatchery that are responding to the monitoring results, so that we're injecting sodium carbonate into the water to basically buffer the water and increase the carbonate ion saturation to make it easier for our oyster larvae to build their shells. And that's really improved our success this past year. And then also we're looking at breeding as an option. We've had a selective breeding program for a number of years here on the West Coast for Pacific oysters, and a couple of the families there have stood out as able to grow better in these corrosive waters. And so we're looking at whether breeding may be an option for us as well. So all those things together have helped us have some optimism that we're going to be able to work around this. Whiskey Creek has learned with the monitoring equipment in their hatchery that if they, you know, they used to come in at 8 o'clock in the morning, turn on the pumps and bring all this corrosive water in, and they've learned with the monitoring equipment, if they wait till afternoon and let the phytoplankton and eelgrass in the bay do their job, they can get much better water in the afternoon. And they know when they get north wind, when the wind shifts to the north, they've got about a 24-hour window before that corrosive water shows up at the intake, so they work around that. They manage around it and have been able to recover a lot of their production just by micromanaging that intake. So talk about the canary in the coal mine. We're often put out there as an example of one of the first industries in the world to really feel the effects of ocean acidification. And as you've heard from Shallon, I'm sure you know, there's a lot of other organisms out there that don't have a spokesman like oyster larvae. So you know, it's just a wake-up call for all the other critters out there that are calcifiers. I think they estimate about 30% of them here in Puget Sound are calcifiers that may be being impacted by the same situation. So, now I'll just finish with this last slide on sea level rise. You know, we have a lot of issues we deal with as a shellfish industry. Ocean acidification is just one of them. Water quality is a big one. Fecal coliform pollution in a lot of our shellfish growing areas. And One of the concerns I have with sea level rise is all these shoreline septic systems that are going to be inundated. The more of these king tides we have, bigger king tides. This is a shellfish farm that I come and go from up in Samish Bay during the king tides in January. That's my truck, my white pickup truck out there. You know, so it also affects our facilities and our ability to come and go. I think it was an advantage this day though, because I was pulling a piece of equipment off my scow, and normally I'd have to drive down on the beach to get it, and this time I pulled the scow up in the parking lot and unloaded it, so it's kind of handy there. So I'll stop there and thanks.